Aloha class, the start of the second half of calculus. Remember, the first half is all about derivatives and finding derivatives and applications with derivatives. And then starting with chapter 5, we'll kind of try to hit up going backwards a little bit, okay? So it gets really interesting. It gets really fun. We really get into the meat of calculus and how we use this stuff every day in the real world. Today, I'm rocking the Sean Capodici Infinity shirt. Just a quick little history lesson for you. One of the biggest reasons why I ended up going to Manuka High School and teaching and coaching was because of Sean Capodici. She was the department head when I first came to Manuka. She was an absolute boss of a leader, unbelievable sense of humor, brilliant lady, great compassion. Unfortunately, she passed away of cancer. I know she still has family in the area. Always much love to the Capodicis and Sean Capodici upstairs. So much love. Always thinking of her and her family. Here we go. 5-1. Let's see what we got here. Topic 6.2, approximating areas with Riemann sums. Okay, and we use geometry and rectangles to kind of give us an introduction of not going forward with derivatives, but now going backwards with derivatives. Okay, you guys? So here we go. Kind of have a nice little introductory here, and it kind of gives us a good understanding of what we're doing here in the second half of AP Calculus. Okay, so suppose from the second to fourth hour of your road trip, you travel with it on cruise control. You 70 miles per hour because you're on 80 and you're rocking it with some of your homies, all right? And you go for a 2-hour stretch. How far have you traveled during this time? All right, let's check this out. So we're going to go for 2 hours, right? And we're going 70 miles per 1 hour. Oh, snap. Bang, bang, choo-choo train. And then I've traveled 140 miles, right, class? Hopefully that was pretty okay. Now B says, hey, can you sketch this? And it says sketch that right there. Well, that would just be a constant, right, class? Now let's make sure I label my axes correct. That'd be V of t, and that'd be time. And I'm going at 70 miles per hour, right, class? And I'm going to go from 2 to 4 hours. It says, is the total distance traveled represented on that graph? Well, is it? Well, you know, it's kind of interesting. I kind of have a rectangle going on here, right? It's kind of a distance of 2, and that's a height of 70. Oh, snap. The area of that is 140. And it would be miles per hour by hour, which gives me 140 miles. So you know what, homie? It does, right? If I do that graphically, pretty interesting, right? I have a velocity graph, and if I do the area of velocity, that kind of gives me the distance traveled, kind of like our position, right? And how much I traveled throughout that time. It's kind of like going backwards, isn't it? Velocity and then something of velocity giving me position. Right? Something to think about there. Okay. For each given velocity function, determine how far you have traveled from the 0 to the 4th hour. And if you look here, I kind of skipped over this, which was kind of important. What if the velocity is not a constant, but what if it is maybe a different type of picture, right? So let's take a look at this. Let's go ahead and graph this velocity curve, right? And that's t, and I would have boom, up 1 over 2, up 1 over 2, right? And I get booyah. And then it's asking me how far did I go from 0 to 1, 2, 3, 4. How far did I go? Now, if we look at that problem before, right, I was able to find out how far I traveled if I found the area underneath the curve. Oh, snap. That happens to be a triangle, which is 1/2 the base times the height, right, class? So let's find the area of that, and I'll bet you it'll give me the total distance traveled. Right, class? So we got 1/2. What's the base? The base would be 4 minus 0, which would be 4. But what the heck is the height? How do I find the height? Well, that's the t value. Just plug that in there and you get 2. And I get 1/2 of 8. And 1/2 of 8 is 4. So 4 was the total distance traveled, right? We had hours. We weren't really given miles. Could have been feet, right, class? So it all depends on what we were talking about in terms of units. But you should always be thinking about units. All right, here we go. We should know how to graph that bad boy, right? That has a vertex of 2, 2, 1, 2, 1, 2, right? 2, 2. It's got a slope of 1, but it is reflection. So instead of going up, 1 over 1, up, 1 over 1, I'm going to go down 1 over 1, down 1 over 1. So boom, down 1 to the right 1, down 1 to the right 1, boom. And it says to find the area over the first 4 spots. So that'd be 1, 2, 3, 4, right? So we're going to find, oh, snap. That happens to be a triangle as well. So that's 1/2 base times height. 1/2, the base is boom. It's from 4 to 0, which is 4. And how high do I go? Well, if I find out how high do I go, that happened at 2, I could plug a 2 into the original. And if I plug a 2 into the original, I get 2. And that answer is 4 also, right? And you also could use a little bit of creativity on this one. And you kind of have a rectangle right there. And you could find the area of the rectangle and subtract out that blues. How about that, homie? Okay, let's do the last one here. It's a parabola, okay? It's t squared. So if I graph this correctly, boom, 1, 1, and then it kind of gets steep, right, class? Oh, snap, and I'm going to go from 0 to 1, 2, 3, 4. Okay, and that would be 4. That'd be 4, 16. Okay, I would do that. Ooh, that's kind of like a, that's a triangle right there, right, class? But if you notice, when I find the area of that triangle, I'm going to have that little extra stuff. And now I'm going to actually make, I'm going to make that extra stuff blue. Okay, blue. So when I find the area of that, it's not going to give me, if I use my geometry skills of 1/2 base times height, because it's kind of like a triangle, right, class? It'd be 1/2, 4 times 16. That'd be 32. Correct, class? But that's not probably going to give me the best idea. So the one thing I noticed is A and B, they were pretty nice straight lines, right? And I was able to find those areas exactly. But I went to C and it was curved a little bit, right, class? I wasn't able to find the area exactly. So obviously, you know, we're in math class. Shoot, we want to be exact, right, class? So how the heck could I be more exact? That is the question. Got an idea, Holmes? Okay. The area problem and the rectangular approximation method. So let's try to use some rectangles. Maybe that might help us out a little bit. Suppose we wanted to know the area of the region bounded by a curve, the x-axis, and x equals A to x equals B. Okay, so we have this region. It's kind of shaded in right there. Okay, we have a step 1, a step 2, and a step 3. Step 1 is to divide your interval, and these are important here, okay? So I'm going to make sure I have these words perfectly set for you guys, okay? Divide the interval, okay, AB into subintervals. Okay, what the heck does that mean? I will show you in a minute, class. I could break it up right there, and then I have 2 subintervals. I could break it up booyah, booyah, equally there, and I have 1, 2, 3. I have 4 subintervals. So that's what it's asking us to do. And step 2 is create rectangles. Why rectangles? Because we all can find the area of a rectangle. That's easy peasy Japanesey, right? So we're going to create rectangles using the width, okay, of each subinterval. And we also need something else, right? But we're going to use the width as the base, okay? And then we have step 3. Use left endpoint, right endpoint, or use the midpoint of each subinterval. Okay, and then 5 would be sum up, sum up. Is that what you do? Add them up. You know, add up all your rectangles. And that's going to give us the area. Okay, oh my gosh, I need a little bit of water. All right, so what I want you guys to do, yum, yum, drink your water. It's good for you, boys and girls. No coffee, bad for you. Okay, we're going to call the left endpoint of each subinterval, we're going to call that LRAM. Why LRAM? Left rectangular approximation method. The right rectangular, we're going to call RRAM, and M is MRAM. Okay, so LRAM would be left rectangular approximation method, R right rectangular approximation method, and M is the midpoint rectangular approximation method. All right, so what I'm going to do right here, if I wanted to draw rectangles using LRAM, I have my subintervals. Here's my first subinterval right there. Okay, that's going to be my width. All right, and then what I am going to do is I'm going to use the left side of that. And if I use the left side of that, I'm going to make a rectangle. Booyah. Okay, here's my next subinterval. I'm going to use the left. Booyah. Here's my next subinterval. I'm going to use the left. Booyah. Here's my next subinterval. I'm going to use the left. Booyah. And then I'm going to color all those in. Find that area, find that area, find that area, find that area. And guess what? That's going to give me an approximation of the area under the curve. Okay, is that a good approximation? That's what you have to think about. That is an example of LRAM. Now, we're going to go through all of them real quickly, actually, right now. Boom. Let's erase that. Boom, boom, boom. Okay, I'm going to make it blue for you guys. Let's do RRAM. What would RRAM be? Let's break this up into, like I said, 4 subintervals. RRAM would be boom right there, but then instead of going to the left, I'm going to go to the right curve and then color in there. There's one rectangle. Here's my next subinterval. Go to the right side. Booyah, that's the next one. Here's my next subinterval. Go to the right endpoint. Ooh, that overestimates that bad boy. Booyah. And then here's my last one. Go up to the right. Booyah. Okay, class, that is called RRAM. Hopefully you have an idea. What the heck is MRAM? Let's do that bad boy. Boom. Okay, what the heck would MRAM look like? I bet you have an idea what to do. I have my subintervals right there. Boom. There's my first subinterval. I'm not going to do left. I'm not going to do right. I'm going to do middle. Okay, so you go to the middle of it. You go straight up. And then you just go and make a rectangle. Color it in. That's the area. Okay, and then add up all those rectangles. Here's my next subinterval. Go to the middle of it. Go up. Booyah, booyah. There's my next guy. Here's my next subinterval. Go to the middle. Go up to the curve. Ooh, a little bit over. A little bit under. You're probably like, this is probably the best estimate. What do you guys think? Go up. Booyah. Booyah. Color that guy in. Add them all up. That is what we call, oh, homie fell. I got you, homie. That's LRAM, RRAM, and MRAM in a nutshell. And if you know how to find the area of a rectangle, easy peasy, Japanesey. All right, here we go. Which method is shown in the 2 graphs below? Hurry up, answer that right now. Hit pause if you need to. Okay, but that's definitely LRAM. Why? Because I have my subintervals and I went up to the left side. Subintervals went up to the left side. Every time up to the left side. The total area under the curve then is approximately equal to the total area of all of the rectangles. Which of the graphs above give you a better approximation of the area under the curve? Why? How could it be further improved? Hit pause and answer that question. Boom. I hope you guys said that this is 100% way better than that guy right there. Why? Because we have more rectangles. How could I get even a better approximation of what's going on? Use even more rectangles, right, class? Hopefully, I'm hoping you're answering these questions on your own. You will learn so much more if you do it. Example 4, illustrate the use of RRAM and MRAM on the graphs below. And it says to use your rectangles. I didn't realize it, but I already did that. So go ahead and practice it right now. Do it again, and you should have the notes on the previous page. So let's keep rolling, okay? Use LRAM to approximate the area under the graph. Ooh, and we're going to go from 1 to 3. All right, so let's go ahead and draw this graph, you guys, so we have it. All right, so we have y equals x squared. That's 0, 0. I'm going to go, we're going to go up to 3. We'll go 1, 1. Okay, what's that? 2, 1, 2, 3, 4. Right? And then 3, 1, 2, 3, 4, 5, 6, 7, 8, 9er. Okay, and let's make that parabola. Okay, boom, right there. All right, so it says to use LRAM, and let's actually find the approximation. So we're going to use LRAM. So how do we do this? So I get an A+ on that pop quiz. That's probably coming up. All right, and we're going to do it from 1 to 3. So that's 1. That's 2, and that's 3. So my length of that is going to be 3 minus 1. So it's going to be a length of 2, but it says to use 4 subintervals. So let's divide that by 4, which would give me a width of 1/2. Whew! So I'm going to have to break these in halves right here, right, class? I kind of don't like my picture there. I apologize, but you guys used a pencil. So let's use 0, 0. Let's use 1, comma 1. We'll go by ones, right? And then 2, we'll use 2, comma 1, 2, 3, 4. Okay. Ooh, 1, comma. Oh, I went up 2, so I better. Ooh, I just want to. Sorry, class. I just want to be this perfect. I want this to be perfect for you guys. Okay, so let's get rid of that. Let's draw this graph again. So we got 0, comma 0. Let's go 1, comma 1. We'll go 2, comma 1, 2, 3, 4. Okay, and then we'll go, so 1, 2, and then we'll go 3 right here. And that's got to be comma 9, so that'd be up there. So there is my graph of my parabola. Ooh, there's tape right there. Okay, but there we go. We got our parabola. Now we're going to go from 1 to 3, and we're going to break it up in subintervals. So that's 3 halves, right, class? 3 halves, sorry. And then that would be 2. So in between that guy, what would that be? That'd be 2.5. That'd be 5 halves, right, class? Okay, so here we go. We're going to break this up, and I have to do left rectangle. So from my first one is going to go from 1 to 3 halves. So I'm going to go up here, boom, right? And then I'm going to go that way and then come down. Okay, so what is that first rectangle? That first rectangle, the area of it would be my width, right, class, which would be 0.5 times the LRAM, which I went up to 1. Okay, and I'm going to write it as 1 squared, right, class, because that's what I did. Okay, I plugged a 1 into the original function because this is y equals x squared. Okay, let's go to the next one. Okay, so width of 0.5 again. I'm going to go up to the curve, right, and then boom, boom, and down. And then I'm going to color that guy in, right, and I have to find that guy's area. Well, that's going to be plus 0.5 times what? 3 halves squared. Everyone follow me? Plus, okay, I'm coming down here now. Let's find the next one because it said 4 rectangles. It's still a width of 0.5, and then I'm going to go up to the curve. Booyah. And I know my curve, it might not be drawn accurately, right, class? And that's going to be 0.5. Ooh, what was that at? That was at 2. So that would be 2 squared or 4. Okay, but I'm showing all the work here for the first one that I do. And then LRAM, the last rectangle, would be there at 5/4. Go up to the curve, booyah, booyah, and come down. And I get all of that guy, right, class? So that would be 0.5, and that would be 5 over 2 quantity squared. And my is, I got it right here, 6.75, right? It'd be units squared, whatever we were talking about. They didn't give us any units, but that would be an example of LRAM. Now, here's something to think about, you guys. Was LRAM, was that a overestimate or underestimate? Okay, and I want you to think about for that a moment because we're going to be talking about that a lot later on. Okay, would that be an under or an overestimate? And I'm hoping you're thinking, well, duh, Mr. Tanaka, that's easily an underestimate because look at all those, look at all that area that we're missing, right? Look at all that stuff, right? Each time we're missing some areas as we go from 1 to 3. Okay, so the interesting thing is, what if we did RRAM? Would that be an over or underestimate? Think about those things. That's how you'll do really well in AP Calc. All right, let's keep moving, right? 25 minutes is my limit, right, class? It says use the previous example, find each approximation for RRAM and MRAM. I want you guys to hit pause and see if you can get it on your own, okay? But hopefully you did this, okay? And I don't have my picture, but each width of the rectangle is 0.5, but this time my R is going to change because I'm going to the right side. So my first right side, right, was 3 halves, but I have to square that, right, class? Okay, plus 0.5. My next rectangle, if I use the right-hand side, that would be at 2. So I'm going to go 2 squared. My next rectangle will be on the right side, and on the right side is 5 halves. And then my last rectangle will use the endpoint, which was 3, and so that would be 3 squared. So I hope you guys did that on your own. I got my answer right here. And if you did all of that math correctly, you get an answer of 10.75, which was an overestimate, right, class, when we thought about it? Now think about this even some more. What if I took the middle? The middle is always the most difficult for students to understand. So make sure you try it right now. Just try the first rectangle. What is the first rectangle going to be? Well, it's definitely going to have a width of 0.5. But what's the height of that rectangle, right? I'm going to draw a little picture here. We go from 1 to 3 over 2, right, class? That was my first interval. And it's still a width of 0.5. But how the heck? I'm not going to use 1. I'm not going to use 3 halves. I'm going to use the middle of those guys. And then remember, that's how we draw that particular rectangle for that piece. Well, what would that be? Believe it or not, that would be 1.25. And I'm going to square that. Make sense, class? And we do that for each one. Okay, so the next one would be 0.5 times, well, let's think about it. It's going to be between 3 halves and 2, right, class? What's between 3 halves, or 1.5, and 2? That'd be 1.75. Kind of makes sense? Plus, now what's between the next ones, which would be between 2 and 2.5, right, class? What's between those? 2.25, right? And we would square it because that gives me the height. And then my last one would be between 2.5 and 3, which would be 2.75 squared. Okay, and then what do I get when I put all that bad boy into my calculators? I get an answer of 8.65, which, how interesting. LRAM was an under, RRAM was an over, MRAM's in the middle, right? All right, here we go. Now, hopefully that made a lot of sense, because let's take it a step further. And what if I give you a table? And people are going to go, oh, no, I'm not good at tables. It's because you don't try it on your own. Okay, try it on your own right now. Using a left Riemann sum with 10 subintervals, estimate the difference traveled by the engine in the first 10 seconds. And I don't want you to graph this. I want you to try to think of it conceptually. And using a table, how could you use LRAM right now using 10 subintervals, which means you need 10 rectangles? What would you do? Hit pause and give it a try. All right, let's roll using LRAM Okay, so my first one is just going to go from 0 to 1. So it's going to have a width of 1. And if I use LRAM, I'm going to use the left side. So if you notice, I'm going to use the 0. Okay, plus my next rectangle is going to go from 1 to 2. Okay, 1 to 2 would be a width of 1. And the height I'm going to use is 12, because I'm going to use the left side, which would be the 1. Okay, and then my next one is going to go from 2 to 3, which is a width of 1. What am I going to use? I'm going to use 22. Because I'd be using the left one, or the smaller one, right, class? Plus, let's go from 3 to 4, which is 1 times 10, right, class? Plus, and I know it's getting a little tedious now, right? 4 to 5 would be 1 times 5, okay? And then what do we go? Plus 5 to 6, a width of 1, a height of 13, 6 to 11, a height of 1, times 11. I think you guys kind of get it, plus, but I'll keep on going because you want complete notes. 7 to 8 is a width of 1. Okay, multiply by the 7, which is 6. And then plus 1, 8 to 9, times 2, plus 9 to 10, equals 6. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 rectangles. And if I add up all those areas, I get an answer of 87. So that means this train, choo-choo train, right, traveled 87, what are we in? 87 inches, right, class? All right, now it gets a little bit tough, and I have to erase here. Ooh, and I need my table. So you know what I'm going to do is I'm going to do this example, and I'm going to show my work up here, okay, class? Actually, over here, okay? Use MRAM. MRAM, only 5 subintervals. Well, shoot, that would be 10 minus 0, because that's how long it is, 10 to 0, right? 10 to 0, and then I'm going to use 5. So that means each subinterval is going to be a width of 2. So what's a width of 2? That'd be 0 to 2, but I'm going to use MRAM, right? MRAM, so I got to use the middle. So my width is 2. What's in the middle? Booyah, 12. Plus 2 to 4, right? Because it's got to be a width of 2, and the middle is 10. Kind of got it, class? Plus, next one, 4 to 6, width of of 13. 6 to 8 is a width of 2, right, for that rectangle, but a height of 6. And then my last and fifth rectangle would go from 8 to 10, which is a width of 2, times the middle guy, which would be 6. You kind of do some magic with your adding and subtracting of stuff, and I get 94 inches. Which one do you think is better? Think about that real quickly, but we are on 2408. Okay, so I got to keep on rolling. Class, guess what works even better than rectangles? Trapezoids! Okay, and so this is really 5, but we put it in here because it's really the same thing. We're going to approximate the area underneath the curve, but instead of using LRAM, RRAM, or MRAM, we have something called the trapezoidal rule, which means you need to know the area of a trapezoid. Okay, so it's really just geometry, but we're going to use this using this example right here, right? We kind of did one earlier where we were dealing with a parabola, but let's say we're doing a parabola again. And we're going to go from 1, okay, to 1, 2, 3. Okay, well, how many subintervals do I want? 4 trapezoids. So once again, 1, we're going to divide it by 4, which means I'm going to have widths of a half. Okay, class, and I have to do trapezoids. Okay, so I'm going to have 4 trapezoids. Let's go ahead and do this guy. We're going to do the trapezoidal rule. That's what this guy is called. We'll go a little trap, 4 little subintervals. What would that approximation be equal to? And I already have these answers, okay? But a trapezoid means we're going to use both heights. Both heights. Connect it, right? Because what is it? It's 1/2 the height. Now, this is the only tough part. The height is always going to be the base there, right? It'd be like taking that trapezoid and flipping it over, okay? So the height of each one of these is 1/2, okay? But then we're going to multiply it base 1 plus base 2. So base 1 would be this height. It'd be plugging a 1 into that function. I got my answers right here to save time, okay, class? So that'd be 1 plus. And then if I was to plug in a 3/2 into that bad boy up there, I would get 1.25. Okay, so that'd be the first trapezoid. Plus, let's do the next trapezoid. I would come up here, touch it with both bases, and connect the dots. You can already notice that's a pretty darn good approximation. And the area of a trapezoid is 1/2 times the height. Remember, the height is the width right there. And then your base is 1.25. We got that from before. But then I also have to plug a 2 in there, right? And if I plug a 2 in there, I get an answer of 2. Okay, plus, here's my next trapezoid. This one here, you go up to the curve. That's base 1. Go up to the curve. That's base 2. You connect the dots. The way you find the area is 1/2. I'll say it again. That is 1/2 because that's the height. Okay, the height, the function value at 2 was 2. But then I'm also now at 5/2. And if I plug a 5/2 in there, I get 3.25. Now I have one more, and if you notice, a trapezoid is an outstanding way to approximate the area underneath the curve. Okay, it's still a height of 1. Why? Because that's the width right there. And then I go my B1, which was 3.25. That's my first base. Add it to my last base, which is plugging a 3 into that function right there, and you get 5. If you add all of that stuff together, you get 4.75. Okay, now I think I'm just barely over 25 minutes. Okay, here we go. So I just got to talk about some things really quickly. I do want you to read this on your own time, but I think the preview of 5.2 is what I want to get to most. Okay, the key to finding the total distance traveled in the last example is similar to the first example, that we break it into the more intervals we have, or the more trapezoids, or the more rectangles we have, the better approximation I'm going to get, right, homie? We want a lot. And the more rectangles or the more trapezoids you have, you're going to get a better approximation of the area under the curve. Now, what I want, that really sounds like something we've already done in calculus. Can you guess what extremely important calculus concept is involved? Aloha! Sean Capodici and the Capodici family, much, much love. Think about you, Sean, and the family every single day. Aloha.